Before we get to the beginnings of nuclear scattering, can you tell me a bit about your coming to Chalk River and when you came here and why?
Yes, that's an easy question and a nice question to answer. I was doing a postdoc at the United Kingdom Atomic Energy Authority at Harwell, and that's where I began my neutron scattering career in 1964. So while I was there doing those experiments, which were in magnetism, Dave Woods, A.D.B. Woods,
Oh, yes.
was on sabbatical at Harwell, and fortunately somebody had turned down an NRC postdoc position in the neutron group. So this came up vacant again, and Dave said to me, would you be interested in applying? So I applied, and fortunately I was lucky enough to get it. So that brought me to Chalk River about a week ago, 56 years ago, in 1966. We got here by train, by boat across the Atlantic, by train up to Chalk River, and we were picked up by a man called Roger Cowley at the station and taken to the staff hotel. And that was the start of it in October 1966.
Who were the starting people here, and when did it really begin?
It began in the late 40s, probably 46, 47. I wrote the long article on the beginnings of neutron scattering at Chalk River because it seemed to me that nobody else was in a better position to research what was going on, and I had the best chance of being able to understand what was done initially. And so I set myself the task, which took a long time, to record the whole history of neutron scattering at Chalk River from the beginning. So the work initially was carried out at the NRX reactor, which was going full steam at that time in the 47 sort of time frame. And the person who was most responsible for the beginning of the neutron scattering program was a man called Don Hurst, who later was head of the Atomic Energy Control Board in Ottawa. But he was the person that was in charge of research with neutrons, and he started doing experiments with neutrons. So most of the early experiments were in the field of nuclear physics rather than solid-state physics.
Right.
Because the interest at that time was probing the ins and outs of the nucleus. So the early work was all focused on the effects of neutron irradiation on the nucleus rather than on the solid-state character of the material. So the first experiments were done, for example, by Hurst and by a man called Alcock, Norman Alcock, for example, on the spin states of the deuteron. And very careful work it was too, which was being done in about 1947, that sort of time. Then they were interested in the measurements of transmission of neutrons through materials and the effect on nuclei. In fact, they were interested in the neutron resonances of several high-absorbing neutron materials, like in the rare earths, gadolinium, dysprosium, samarium, europium, possibly for control rod purposes. They wanted to know how well it worked. So the way this was done at Chalk River was using a crystal spectrometer. So the neutrons fell on a single crystal, actually usually at that point a natural single crystal, and the takeoff angle of the neutrons from the reactor gave them the energy of the neutron, and measurements were made over a wavelength range from 50 electron volts, very small angles, to about 1 milli-electron volt at relatively high angles. And one of the interesting things they found was that the resonances followed the Bright-Wigner formula really pretty well, except as the atomic mass of the material they were examining came down, the deviations from the Bright-Wigner law became more apparent. And it was guessed by Brockhaus and Hurst that this was due to inelastic scattering in the material, which changed the wavelength of the neutrons before it hit the nucleus and gave a resonant result. So that was sort of one beginning hint that in fact there was inelastic scattering going on, and it could be seen at NRX. Now, Hurst hired Bert Brockhaus in 1951 from the University of Toronto. He'd just finished his PhD, and then also hired Dave Henshaw a year later in 1952 to work with him. So Henshaw was Hurst was particularly interested in liquids, and the field that Henshaw and Hurst entered was the measurement of the structure of liquids rather than the structure of solids.
Okay.
And also Henshaw was very good at growing single crystals, it turned out. And so that became a very important thing to do, to grow single crystals of materials like aluminium and lead, rather than, and use these for monochromators to give a beam of a known wavelength, rather than natural crystals, because they were a lot more efficient at doing that. So one of the other early areas was measurement of neutron scattering from gases, for example, like oxygen, O2, and CO2. And they were fortunate to have at the lab at the time two scientists who were very interested in scattering from nuclear systems, because the scattering was from, of course, the nucleus in a gas. And this was a man called John Spears from Cambridge, and he had done calculations of the scattering from two nuclei coupled together, as in O2, for example. And they found that the experimental results could be quite well described by this pair of scatterers close together in the case of O2. So that was the sort of starting point for the measurements that turned into inelastic scattering.
Uh-huh.
Initially, the measurements were all interested in the measurements were focused on nuclear physics. Now, Hurst was also very much aware of what was going on elsewhere, and he worked on the crystal structure of sodium ammonium chloride, deuterated ammonium chloride, and he worked with scientists from Imperial College London on measuring the structure. So she must have recognized that he was doing this kind of work and came over and joined for a couple of years to work with him. So the early people in the game were Hurst. He went on to much greater things. Then Norman Zincock, Norman Alcock, who later was famed for his work on disarmament when he left Chalk River, nuclear disarmament, and the pugwash movement. So he became a member of the Order of Canada because of his contributions to disarmament, which was quite interesting.
Uh-huh.
And John Spears went back to Cambridge. Another person who was there very early in those early days was a man called Noel Pope, who was very interested in the formalism. He's a theoretician, very interested in the formalism of the neutron scattering, and he was a great help in formulating how all this should be done. He later became a professor at the Royal Military College in Kingston. So that was the beginning of the early work in neutron scattering. So Brockhaus came in 1951, and the other scientists were already here: Pope and Spears and Alcock, and that's where it started.
Right. Both NRX initially and then a few years later NRU were sort of world leading neutron sources, so that probably brought a lot more people to come to Chalk River to do the investigations.
that was certainly one aspect of the situation. The other was the excellence of the staff using those neutrons at NRX and then later NRU. So the thing that made Chalk River stand out remarkably well was the fact that they had developed something called the triple axis crystal spectrometer, which Brockhaus developed, and measurements were made with Stewart on measurements of phonons in aluminium. That's a bit later. Let's just skip back just one moment to 1950. There was a meeting of Brockhaus, Hurst, Pope, and Trudy Goldschmidt on the possibility of doing inelastic scattering. And they recognized that NRX was probably enough flux to be able to do it, but they had to improve their experimental techniques. They had to get more neutrons onto the sample. They had to have better shielding in order to be able to measure that inelastic scattering. But this sort of study group on neutrons by this group of scientists, it's referred to several times in the literature, was really very, very important for Chalk River because it became the leader in inelastic scattering. So the particular piece of equipment called the triple axis crystal spectrometer, you create a monochromatic beam for which you know the initial energy and equivalently wavelength, and you measure the scattered neutrons and measure their wavelength as well. So with those two facts, you can work out the energy that is given to the sample when you create for example, a lattice vibration in the sample. So it was the fact that you could do a controlled experiment, a very nicely controlled experiment, with the triple axis crystal spectrometer on a material, on a single crystal, very important to have a single crystal, and then you can measure the energy loss of the neutron, and consequently the energy gain of the excitation that you've created. But you know the wavelength of the excitation as well that you've created, and that allows you to map out the energy versus the wave vector, energy versus wavelength relation for a material. So the first one that was Alex Stewart did with first material looked at was aluminium, and when you read the paper you realize how extraordinarily careful they were in doing the experiments. So one of the things that characterized Chalk River was the care with which the experiments had been done. So there are many ways you can get peaks with a triple axis crystal spectrometer that are nothing to do with inelastic scattering, all to do with other processes in the sample. Complicated processes, but easy to work out what they are and whether the little spurious peak that you see is really a lattice vibration or whether it's something spurious. So they'd worked out all these funny peaks that they got when they didn't expect them, and understood where they all came from. So that was one of the things that marked the early experiments of Brockhaus and Alex Stewart, was the care in which they'd done the experiments. Not only did they do it by crystal spectrometry, but they also set up a time of flight diffractometer and showed that you got exactly the same result with time of flight, knowing where the lattice vibration actually was going to come in energy, because you could then figure out exactly how you should do the experiment to see it. So they'd done very, very many checks like that. They'd done it by different techniques. They'd done it on different crystals, and everything sort of superposed on together to make a complete story. So that was very, very important, the skill of the people doing it. Then not only did they do the measurement, which is challenging enough, but they also worked out how to interpret the results. So the initial idea is that you have nuclei, or the atoms, strung together with spin constants in the material. And by looking at the spectrum of scattered neutrons, the inelastic scattering spectrum, you can work out what the spin constants are in different directions between the atoms at different positions. So not only had they got their head round doing the experiments properly, but they also figured out exactly what it all meant in terms of, the physical properties of the material.
Right.
Now, I mean, looking at it from 60 years later or something like that, there haven't really been terribly many very convincing theories about the origins of the spin constants in terms of the electronic structure of the material. But eventually that will come.
Right.
So there was this tremendous interest in measuring excitations in materials. So many elements were looked at to look at how simple the phonons looked and how it related to the electronic structure of the material. Say materials like sodium, which only has one atom outside a closed shell, and so on. Of course, as time went on, you tried to do more and more complicated things. So instead of one atom per unit cell, you looked at materials with 2 atoms per unit cell. And then you get, in addition to 3 acoustic branches, because the long wavelength end of the phonon dispersion relation, or vibrational dispersion relation, is actually the velocity of sound. So of course you can measure the velocity of sound, and you go then to check that the measurements you make at large wavelengths, small q, actually match very nicely the velocity of sound in those crystals. So all this sounds very, very sort of specialized, and in fact probably my talk is one of the more specialized talks that you will get from old timers. So I don't have a vast purview of the company, but we were, or they were in that time, very good at exploiting this knowledge and the skill they had.
Right.
Now, not only did they measure lattice vibrations in crystals, but they also guessed that there would be similar relationships for magnetic materials, ferromagnetic materials, or ferrimagnetic materials as well. So the analogous excitation in those cases is called a spin wave. And in fact, Brockhaus got hold of magnetite, a natural crystal of magnetite, and showed, sure enough, there were magnetic excitations of the spin system in magnetite. And then he did an incredibly difficult experiment on the alloy cobalt iron. So cobalt has a hexagonal close packed structure, but if you add iron to it, you can persuade it to become body-centered.
Uh-huh.
And if you have, for example, 5% iron in cobalt, you can grow single crystals of the body-centered cubic structure. And as a result of that, they were able to show that there were spin waves in cobalt iron as well, in a metal, which was a revolutionary thought, because the initial thought was that metals were just electrons whizzing around, and there wouldn't be these collective excitations of the spin system. But there they were there quite clearly. And that was an extraordinarily difficult experiment to do, because cobalt is a very high neutron absorber. So you have to be very careful how you do it. And also, the dispersion relationship is very steep, because the coupling between the spin systems is very high. So the dispersion relation for spin waves goes up very, very fast, and is very hard to measure accurately. And he'd done a darn good job in getting at that, knowing all these difficult things. So the other thing that they did was looked at the excitation of just about any system that existed. So, for example, in the paramagnetic state, above the Curie temperature of a ferromagnet, for example, there is still magnetic scattering. So they measured the magnetic scattering in manganese oxide, for example, in the paramagnetic state. They also were cranking up work on liquids as well. So they were doing measurements on water. Brockhaus had done measurements on water, and that was a major contribution, because water, of course, is the moderator for neutrons in the reactor, heavy water, but light water is also used in the American reactors. So understanding the motions of a liquid was very, very important. And so the discussion of the work they had done on light water and heavy water by Brockhaus was extremely, extremely careful. He'd done very, very careful measurements and was very, very careful not to overdo the explanation, but recognize what could be shown quite clearly from the nature of the results. So the questions were, in the matter of water, what was the nature of the vibrations in water? And the answer came that it was a mixture of two kinds of vibration. One was a diffusive motion of the water molecules in water, and then there was a possibility also of jumping, so that in addition to sort of slow diffusion all the time, there was a jump structure, and Brockhaus was able to show that in fact diffusive motion was very important, but there was also a jump component too in the case of water. So all those things were what made Chalk River famous. The fact that they developed the triple axis crystal spectrometer, and the fact that they developed the constant Q technique to do measurements on single crystals meant that Chalk River was way, way ahead in doing the experiments and doing the theory that went with it to understand the spring constants in regular metals due to that govern the vibrational spectrum, and also the stiffness of the exchange forces between spins that make up a ferromagnet. So that the measurements that Brockhaus had made in the period between 1951 and 1962, when he left, were enormous. I mean, he must have worked like very, very hard to get all this work done, and he measured the first excitation in just about any system that you might care to think about.
He was a phenomenal person that was quickly recognized as well.
He was quickly recognized, but he also gave super talks as well.
Right.
And he certainly had a very strong opinion about how you should do experiments. If you were an experimentalist, you had to bust a gut to make sure that your experiment was correct, and that you had, you'd eliminated any possibility of any errors, and that you'd done very well in understanding what was the origin of those excitations.
Right.
So,
in 1962-63, McMaster succeeded in inducing Brockhaus to move from Chalk River. What type of an impact did that really have on the programs here?
My own feeling is that they developed in a natural way. In other words, as time went on, the problems tackled got more and more complicated, and so you were dealing with more branches of the experimental spectrum, of the excitations in phonons, and more difficult measurements of the dispersion relation of spin waves in materials. One of the complications that I mentioned earlier of more complicated materials was looking at alkali halides. So the obvious one is common salt, sodium chloride, but a better example was potassium chloride. And Dave Woods, who was hired in 1957, worked on phonons in general, phonons in the various elements, but he also worked on phonons in sodium chloride, and particularly potassium chloride, Now, sodium chloride is very difficult to look at because sodium has a very high incoherent scattering cross-section. That is, there's random scattering from the sodium nuclei that's very strong. It's about 5 barns or something. So this then causes difficulties because you see not only the sharp phonons, but you also see a diffuse background coming from this incoherent elastic scattering. That makes it really quite troublesome. But what they did establish was that one particular mode in potassium chloride, which doesn't have this problem because it's not sodium, and they are able therefore to get much better results, was that one of the branches was quite anomalous in the sense that the peaks of the phonons were really very broad, in fact not that simple, maybe 2 peaks in it, and that was hard to understand. Now, one of the visitors from away that was very, very important from the point of view of understanding alkali halides and other problems which I'll come to was a man called Bill Cochrane from Cambridge. He later became professor of physics at Edinburgh, but he was involved, for example, with Crick and Watson in understanding the spiral structures. They went to Bill Cochrane to understand what the diffraction from spiral structures would look like, and Bill was able to tell them because he was a real whiz. Anyway, he was very interested in anharmonicity, that is, the departures of the well, the potential well between atoms in crystals from parabolic. So there are extra terms in the expression for the energy because of the anharmonicity. Now, what that might mean in practice is, as the temperature goes up in a metal towards the melting point, there's a lot more excitations going on, and the phonons start interacting with one another, so they become broadened. So in fact, one of his students, or his student, Roger Cowley, who comes into the story very strongly later on, was very, very good at the mathematics of green functions and understanding metals in that way. And he came up with a theory for anharmonicity that matched really very beautifully the results, the anomalous results they got for that one branch in potassium chloride. So that more or less established the importance of anharmonicity in looking at the phonons and understanding their spectrum. So that was very, very important, Bill Cochrane's work. And he'd originally heard Bert give a talk at Brookhaven and spoke to him afterwards and said, you know, can I help with this? And that's how it all began. He spent a whole year at Chalk River helping with this. So now we come to the time when Brockhaus had left and the beginning of the 60s. So at that time there were a lot of new staff, so Dave Woods was already working. Gerald Dolling came in 1961. Right. Roger Cowley spent a year here, not on the staff but as a student, in 1961. And he particularly worked on a complicated material, a ferroelectric, called strontium titanate. Now, strontium titanate undergoes a phase transition, a crystallographic phase transition at a particular temperature, below room temperature. And when that happens, you go from a cubic perovskite to a distorted cubic perovskite. And Bill Cochrane had worked on a theory of the instability of crystal phases, and he'd come up with the picture that there should be a situation where one phonon, as the temperature went down, would soften, would get smaller and smaller and smaller, and in fact eventually go to zero. And if it went to zero, there were so many phonons of that wavelength that the crystal felt that it had to change to that new structure. So that was the soft phonon theory. And Roger spent time this year at Chalk River observing this one particular phonon in strontium titanate staggering towards zero as you lowered the temperature towards the point where it goes into this distorted structure. So that was very, very important. Bill Cochrane's contributions and Roger's contributions in understanding the instability of crystal phases and the connection with phonons. Now it's a bit more complicated than that as things turned out, because there's not only that soft phonon picture of things happening, but also there's another picture whereby the structure that it finally takes at low temperatures is heralded by scattering at the elastic point as well. So there's elastic scattering as well as phonon scattering that sort of predates the phase transition. And it's a bit hard to tell whether it's soft phonon or some sort of diffusive motion that causes or jump motion that causes the phase change. So that's the sort of complications that...
Nothing comes very simple.
No, nothing comes very simply. It was always these two possibilities. And of course, over a period of probably 10 to 15 years in the late 60s and early 70s, a lot of work was done throughout the world, particularly at Brookhaven, on the stability of phases. The important thing was to have a single crystal. If you had a single crystal of this material, then you could do the experiment and check it out, what sort of mode it followed. Was it this diffusive mode, or was it a phonon mode softening? And both usually happen together. So it's a bit hard to unscramble what's what.
Right.
But Brookhaven had managed to get all these single crystals from Bell Research at Murray Hill. And so really they had the upper hand there because they could always get hold of these single crystals.
Right.
So nobody else really got a look in there. But strontium titanate was the first example, and it was a very clear example of a mode softening. So that was Roger in 61. Gerald Dolling came in 1961 as well, and he was a real expert on using symmetry to simplify the interpretation of results in complicated solids. So one of the complicated solids they looked at, of course, was uranium oxide. They had a big single crystal of uranium oxide, and of course that's used in fuel elements in the CANDU, so it was very relevant. And Gerald used his symmetry arguments to simplify the understanding of the spectrum by essentially, if you take the symmetry into consideration, you can sort of factorize the matrices that occur in the matrix formulation for the spring forces between the atoms. And instead of having a huge big matrix to solve to get the frequencies of the modes or the energies of the modes, you can break it down to a number of smaller matrices which are easier to solve. And remember, in those days, solving a matrix wasn't as easy as it is these days. So the use of symmetry to simplify the understanding was a very important thing, and Gerald was very good at that. So he also did a lot of work on phonons as well. Now then, the other people that came were Brian Powell in 1963, and then Bill Byers in 1965, Eric Svensson in 1964. Now Eric was interesting because he was Bert's first student. And
yes,
right.
Ethnic master.
Yeah.
In fact, Eric and I overlapped a bit then.
Oh, okay. So Eric was one of Bert's first students, along with Mike Rowe, and he joined the staff after doing measurements up at Chalk River for his PhD. Bill Byers came in 1965. Brian Powell's speciality was complicated organic materials, so hexamethylene tetramine, which has probably 6 or 7, 8 atoms per unit cell, and it really gets quite complicated because that means there's a lot of branches of the dispersion relation, and where to look for them and where to find those branches and identify them starts getting very difficult. So you need to do the measurements, calculate a model, then try and decide from the model where to look, and then look there. But he was a specialist in that. He'd come from Queen Mary College in London. And I appeared in 1966 as a postdoc, as I explained right at the beginning. So by that time, Roger and Bill were working on cobalt salts. So the early measurements on spin waves had all been on very simple materials like manganese fluoride, etc., and the ferrites, for example, which are not quite as easy as I've suggested. Actually, they're fairly complex in detail. Anyway, cobalt salts are a bit different because not only is there spin angular momentum, but there's also orbital angular momentum, and that causes quite a difference. It means, in fact, there's going to be several branches of the dispersion relationship, even though you've got one atom per unit cell. So, in fact, in cobalt oxide, they saw 3 branches, but the trouble with cobalt oxide is it has a very awkward domain structure. So the spins in cobalt oxide are along the cube edges, and that means there can be 3 possible domains corresponding to 3 edges of the unit cell.
Right.
So you're never quite sure, in the case of magnetism, well, you're getting signals from all 3 domains at once, and it's very, very difficult to untangle them. It's very hard to get a single domain, single crystal of an antiferromagnet, cobalt oxide, and so the results on cobalt oxide were very hard to get at. However, then they tried cobalt fluoride, and cobalt fluoride is a lot simpler than that. There's not a serious domain problem because of the structure. It's not cubic, but it's not orthorhombic, it's tetragonal. And so that makes it a great deal easier. The domain problem is made a lot simpler, and they were able to measure the spin waves in cobalt fluoride. Roger came up with a wonderful way of attacking the interpretation of this problem by taking into account the spin as well as the orbital angular momentum of the cobalt ions, cobalt 2+ ions. And they were able to come up with a theory that called the many-level spin wave model that gave a very good description in terms of the spin-orbit coupling in cobalt fluoride and the exchange interactions between the cobalt ions of the branches of the dispersion relation. And that was a pretty important development. So that was, again, one of Roger's contributions to the skill and the reputation of Chalk River. Bill worked with Roger on cobalt fluoride, and Peter Martell also worked in that field. Now, at the same time, the work on liquid helium was getting more and more attention from Dave Woods, and Eric Svensson joined Dave in doing experiments on inelastic scattering from liquid helium. In fact, one of the particular questions they were trying to answer was, what is the fraction of superfluid helium when in the material when it becomes a superfluid? What's the fraction of superflowing helium atoms in the material? And it's not, they don't all become super. Yes. Only about 10% do. And it's a matter of trying to find out what those 10% were. So by that time also they'd measured the dispersion relationship in liquid helium, which is quite surprising since it's a random solid, it's a liquid. So it's random, it's a liquid. And they found that in fact there are 2 contributions to the peaks which were sharp, surprisingly. One was the phonon contribution corresponding to the velocity of sound in helium, because of course there is a velocity of sound in helium. But then in addition, liquid helium, when it becomes superfluid, there are very complicated twisting motions of the helium atoms, and they're called rotons. Rotons signifying there's some sort of rotating component to it. So they'd seen how the phonon part and the roton part fitted together, and that in fact the roton part gradually disappeared. the understanding of that came rather later. So there's a huge amount of work done in that time period, beginning on liquid helium. So when I came, my interest was in magnetism because I'd done magnetic studies at Harwell in England, and so I joined in the effort on in these materials. The ones we looked at, the materials we looked at, or the question we looked at was what are the excitations in, for example, manganese fluoride when you add a little bit of zinc instead of manganese? So you've made an alloy material. The spins are all localized in manganese fluoride with zinc in it, but you're going to upset the spin wave spectrum of the manganese. So it's understanding the nature of the perturbation that you've put on the system by adding an impurity. So there are two cases there. One is when you put an impurity in it that has a characteristic spin wave spectrum of its own that doesn't necessarily fall in the band of spin waves of the host. So cobalt in manganese fluoride produces a peak outside the spectrum of the manganese fluoride. So that gives rise to a local mode. So you see an excitation on the cobalt, and you also see the complete excitation in the manganese, but they're separate. One is a local mode. It doesn't overlap with the manganese modes, and that's the situation there, the local mode. When you put zinc in manganese fluoride, you have a different situation, and it's best visualized by saying, I have a manganese now that has, instead of 6 manganese neighbors, it has 5 manganese neighbors, because one of them is a zinc.
Okay.
So where would you expect that to appear? Well, you expect it to appear at 5/6 of the maximum energy in manganese fluoride, and that's where you see it. You see a perturbation of the spin wave spectrum there that gives rise to a shift in spin wave energies and also to a width in the spin wave energy. It's right there, it's a 5/6. So the easy way to understand it is that you've got excitations on the manganese now with one zinc neighbor, so that the molecular field that the manganese is in is now less. But it gives rise to a resonant mode which perturbs the distribution of the dispersion relationship in the manganese.
Ah.
So that was very interesting. That's called a diffusive mode. So I started with that, with Roger and Bill, and actually Eric Svensson too, on doing those measurements on alloys. And we checked it out in different alloy systems, and that worked very well, and I was very happy doing that, and I learned a lot of how to interpret these situations with spin as well as orbital angular momentum. The other thing I started to work on was the rare earth metals at low temperatures, in particular holmium and erbium. So these have exotic magnetic structures at low temperatures. The spins are arranged in a cone along the hexagonal axis of the hexagonal structures. So instead of being along the hexagonal axis, they're inclined at an angle. And so as you go up the chain, the angle's changing, rotating in a spiral fashion. So the question is, what is the dispersion relation going to look like? And is there another question we asked was, is there a relationship between the frequency or the energy of those modes and a lower state? As you lower the temperature, you get a phase change in that spin structure. And does the change in the excitation spectrum tell you about the symmetry of the lower energy phase? There was a change, but it wasn't convincing, really. So I worked with Brian Powell on that problem, holmium and erbium, and Dave Woods, who was also interested in that. Now the sad thing is that we had to use natural samples of holmium and erbium. Erbium is quite a high absorber, but if you prepare isotopically pure erbium, you can get rid of that absorption cross-section. And Oak Ridge did that. They grew single crystals of isotopic erbium. And
supply was easier
supply
at Oak
was
Ridge.
easy, yeah. Supply was easy at Oak Ridge because they had all sorts of possibilities for doing that.
Right.
Like also preparing nickel from nickel 62 instead of natural nickel. So you can get rid of the incoherent scattering, which
Right.
makes life a lot easier and makes the experiments a great deal easier to do. So that we sort of got beaten on over the head in the case of erbium because Oak Ridge had these lovely isotopic crystals. And there you go, you win some, you lose some.
Yes.
Right. So that was the beginning of my career at Chalk River, and I did magnetism, did paramagnetic scattering and rare earths, spin waves in rare earths, temperature dependence of the spin waves in rare earths a bit below the phase transition, and this work on alloys as well.
Most of the work up to this point that you've described has been on materials that are sort of academically interesting, but the pressure seemed to always come about what relevance has it to industry and things of that manner. So there really was a push beginning to look at materials other than Gerald was looking at uranium oxide, and,
Yes.
and you got into that fairly heavily with Stuart McEwen and
I did, yes,
a
I
group
did.
that way.
Well, it was a worldwide phenomenon. Actually, it wasn't just Chalk River. In fact, other countries, other labs were way ahead. Britain, for example, was way ahead of us in withdrawing funding for doing pure basic research. People were asking, you've got this super neutron source. What can you do to make use of that will be useful? So it turns out, yes, there is a really useful thing you can do. And the concept is we're going to use neutron diffraction as a strain gauge to measure the residual strain, or the strain in a material, through the thickness of the material, because neutrons easily penetrate. For example, an inch of steel, it gets a bit difficult when it gets to 2 inches of steel, but you can go all the way through 1 inch of steel quite readily. Zirconium, tons of it, because it doesn't have a high absorption cross-section or anything like that. Nickel is tricky because it has a large incoherent cross-section, which makes the signal weaker relatively. So the idea was that we could use neutron diffraction as a strain gauge to measure strains in engineering components. That was the notion. Now, how do you do that? Well, you set up your spectrometer so that you create a little voxel, a little box, right in the center of the table, center of the apparatus, the sample table, and then you have a translator table on top of the regular angular table, and then you put your sample on that, and you move your sample through the little voxel, and that way you can map out the strain as a function of position in the crystal in a particular direction. If for example, a weld has a direction, it's the weld direction. So you can look in the weld direction and the two directions perpendicular to that. So now we have a strain gauge that is quite useful for looking at the strains in engineering components as a function of direction. You just have to twirl the sample around through 90 degrees and then through 90 and 90 the other way. So you can get 3 directions of strains and work out the stresses. So we had seen that done. The first measurements of that kind were done in late 70s, like 77. So that had been done in Missouri, the little reactor at Missouri by Aaron Krawitz, and also in Germany. So we knew it, and also at Harwell. So we knew it could be done. But it was a matter of can we make a tool to do that with the equipment we've got. So immediately you realize you've got a tool like that, you want to look at topics of interest to AECL, which we did. So at that time there was a big problem with overrolled pressure tubes. So the pressure tube is encased in an end fitting, and you run a mandrel into the tube and it squeezes the pressure tube into grooves to make a watertight seal. Now if the mandrel goes too far, so that you're straining the zirconium when it's not supported by the end fitting, you get a big stress there. And then, because you have that big stress there, you get a crack there in due course. And that's in fact what happened in one of the series of power reactors. They found cracks where the mandrel had gone too far and the tube had been overrolled. So there was a great problem with that, understanding the cracks that formed in zircon-niobium alloys, the pressure tube alloys. We were able to get hold, well, there was a lot of work done, measure the stresses in end fittings and end fittings plus beam tubes. And mock-ups had been made of this overrolled pressure tube. So we weren't looking at an active sample, but we looked at the mock-ups that had been used in mechanical engineering to try and measure the stresses by the destructive methods or by X-rays. So here was a question. You had this rather heavy object that might weigh 70 pounds or something like that, and you've got to put it on top of your spectrometer and move it with a precision of millimeters, and by small steps of order millimeters, with a rather weak positional encoder, positional translator table. So how do you handle that? Because the translator tables were kind of flimsy. They weren't intended to take 60 or 70 pounds.
By now all of this work was in NRU?
Is NRU.
Yes.
All this work was in NRU at that point. And so what we decided to do is adopt Egyptian technology and create a balance bar. So the short arm of the bar supported the heavy end fitting and the zircon-niobium pressure tube in it, and then the long arm had a counterweight. So in that way you could get around the problem of the heavy sample on a rather weak translator table and move it accurately. So that's what we started with, and we were very happy that the millwrights at NRU were able to put together a beam balance for us that worked like a treat. And immediately we did the experiments, we realized that in fact we could measure those stresses in the zircon-niobium pressure tube through the end fitting relatively easily. It wasn't a hard experiment at all. Now it's helped by the fact that zircon-niobium has a strong texture. That is, the crystals in the material are oriented in a particular fashion, deliberately. But because of that, we were able to measure the stresses in the zircon-niobium where it had been overrolled. So that was the first thing. And the other thing is we had very good relationship with the people in metallurgy. So people that spring to mind are Rick Holt and Bob Hosbons,
Oh yes.
and of course Stuart McEwen. Interestingly enough, Stuart was on sabbatical at Argonne National Lab, and he was interested, of course he was interested in zircaloys. So he'd taken a series of samples of zircaloy that were strained to different amounts and then unstrained, but he had a series of samples of that had gone through this series of steps, and he looked at them with the time of flight spectrometer at the Argonne, and sure enough saw very clearly what was happening to the strain state of the zircaloy when he'd given all these different mechanical treatments. So we learnt of this through a progress report, and we thought, well, we should get on this game too. So that's when we started trying to work out how we could do these measurements at Chalk River. So the other thing they helped us with enormously was identifying problems that were of interest to the Canadian nuclear power program. One of the problems of interest was the fact that in a steam generator, the steam goes through narrow tubes and they're bent at the top because the steam comes in and it goes round and round and round.
Right.
So there are bends in these tubes, and where there are bends, there are stresses, and cracks tend to develop. And if you have a crack in a steam generator tube, you just got to block it off. So it's very important to understand where those stresses were and how big they were. So we looked at that too. Rick Holt had done that with X-rays, but we thought, well, we should be able to try and do that with neutrons. And we were able to do that too very readily. Look at the stresses as a function of position around the diameter of the tube, and you see where the stresses are highest, and they are exactly where you expect from a mechanical point of view, and they are very high in materials like Monel and Inconel, for example, which are of interest in the steam generator business. So having done those kinds of starting experiments that were of interest at ACL, we saw that we had a tool that was really very, very useful in an industrial context, and you could more or less tackle any problem you wanted with the neutron setup we had. So that was the beginning of what was called the Andy business, the applications of neutrons application of neutron diffraction to industry. Andy, that's what that stands for. And very quickly, since the commercial office had just cranked up at that time, a big push to commercialize, there was a lot of help from them in setting up booths at conferences and giving talks. And since we were the first ones in North America to start making an industrial tool of this, there was a lot of interest in industry from what we could do. So we got a lot of business really very quickly, mostly from the United States. So the things that spring to mind are looking at uranium welds, for example. It's unusual to have a weld in a uranium. No, actually they were uranium tubulars rather than welds. We'll come to the welds later. And these tubulars had been heated up and quenched to give the correct residual stress on the outside where any gases were going. And we were able to do experiments on these uranium tubulars with great ease. I mean, it was very, very easy. And the nuclear side of it was handled by Nuclear Materials Control. They got all the samples. We asked for one, and they bring it up to NIU, and then we'd do the experiment, take it off, give it back to them, and get another one. And so, because of course, when you have uranium tubulars, you have fissionable material on the main floor, and there's a limit to how much you can have. But all that worked really, really, really well. And of course, a little bit of neutron diffraction doesn't really make the material active. So that worked really, really well. Now all that went into the open literature. Then the other piece of work we did, which is kind of characteristic of the sort of things you can do, is if you take a stainless steel disc and then you squeeze it along the north-south axis, you squeeze it this way, then beyond the yield point, so you've gone beyond the elastic limit and you started distorting it plastically, what you're going to do is you end up with a residual stress in that disc when you've unloaded it. So people were able to calculate this from the finite element models of the material, and in fact you can then do a measurement on that stainless steel disc and see whether the calculations match the experiment. And therefore, if the experiment does match the experiment, you've got things right, and if it doesn't...
calibration points.
Yeah, it's a good calibration point. So that's a very important exercise to do, to go through that and check that it matches the experiment. So that was another thing we did. So immediately Another great thing we did, which I really enjoyed, was we hung up a 36-inch pipeline, inch-thick steel, on the spectrometer, beam balance, and we're able to measure the stresses in that weld. It was a welded
Right.
line pipe, and show what the stresses were, and show that they were really quite high and quite important in a weld. So that was good because it was a macroscopic thing, and it was a big weld and
Fair-sized object.
fair-sized object on the spectrometer. So that's where that went, and the Andy business, after a few years, was making a revenue, not a profit, of up to $500,000 a year of commercial work, fee-for-service research. The interesting thing was it was easy to estimate how long it was going to do the measurements. The tricky thing was how fast you were going to be able to do the results, get the results out and
Right.
understand them. So that was very good training, actually, because in an industrial context, they want to know the result tomorrow, not in 3 weeks' time. So you had to adjust your way of thinking to say, yeah, I'm going to get the main points out really, really quickly, and we'll follow up with the details later on. So that was very good. It's a very good lesson to learn in doing applied physics. You have to know what you're doing immediately, or get the big things right immediately.
Right.
So we worked with Pratt & Whitney and other groups as well.
That was looking at blades on rotors for planes?
Well, yes, there are two things there. I'm going to mention two things. The work on with Pratt & Whitney was on a turbine disc, and one particular variety of turbine disc by one particular manufacturer always seemed to develop cracks, and they didn't understand why. The material looked the same, metallography was the same, etc., etc., etc. So they said, can you look at it and see what's wrong with it? Well, we did, and it was a quite easy experiment to do, because you looked at the intensity of one particular reflection in the material as a function of position round the turbine disc. And we found, in fact, there was a fourfold variation as you went round the disc. And we didn't know what that meant, but when we showed it to the people at Pratt & Whitney, they said, oh yeah, that's very clear what's happened. We asked for the disc to be clock rolled. That is, every few degrees you squeeze it, or every few degrees you roll it. But they hadn't done. They'd done it in two parts. They rolled it this way and that way. And so you have fourfold variation instead of nearly no variation all the way around. So it was really, really quite remarkable that neutrons, just by looking at the intensity as you
Right.
went around the disk, you could spot what was wrong, or they could spot what was wrong from your result. I mean, I didn't know what to expect at all. But that was one of the interesting points we found. So the other interesting thing about the work with Pratt & Whitney, there was a big contract with Wright-Patterson in the Air Force Base in Ohio. And we said that we think we can measure temperature non-invasively in a turbine disc. And how would you do that? Well, there's two ways of doing it. You measure the lattice expansion, but the problem with that is you can get stresses as well in the rotating turbine disc as it rotates. So you can't untangle the stress from the centripetal forces from the temperature, from the strain due to the temperature change. So you can't use neutron diffraction and the position of the peak. But what you can use is neutron diffraction and the intensity of the peak as a function of temperature, because that follows a curve that's generated by the Debye-Waller factor in the intensity of the material. So if you can get the Debye-Waller factor of the material, and then look and see how the intensity changed as a function of temperature, you can measure temperatures in this way, non-destructively, inside an engine. So that was the notion. That was the concept. Well, it was a lovely, lovely concept. And in fact, in simple cases, it did work. You could measure temperature to about plus or minus 5 degrees as you raise the temperature. But the problem was the materials which turbine blades are made of, they tend to be face-center cubic stainless steel. And that grows single crystals very, very easily. So the grain size is very high. And in doing the rotation, doing a measurement of the intensity, the fluctuations as you go around around the disk are so great because of the variations of the number of grains in the little voxel,
Right.
that it completely throws out the accuracy of the measurement. So in fact it turned out that we couldn't do it. Now the concept was originally, my picture was we'd have an engine, a running engine in NRU, and do the experiment on a running engine. So that would have been...
That probably frightened a few people.
It did. Well, one of the questions was the noise would be horrendous. Oh, he said, well, you just build a little wooden hut around it all to absorb the noise. The other thing, what was a bit worse than that, was the engine uses a lot of air. So it sucks, it's a vacuum cleaner. So it would suck the nasties off the top of the reactor.
Right.
And so that was not so good. You couldn't, what would you do with that? Well, you certainly have to put the exhaust out through the window. You could do that, but the vacuum cleaner aspects are a bit more difficult. But the thing that really killed us was making the safety case that a turbine blade wouldn't come off the disk and fly up the beam into the reactor. So the possibility of making that safety case was so so difficult that
daunting.
Yeah, we just didn't even try it. But you have to try.
Yes.
But we had an engine up on the spectrometer, and we showed that we could find the internal components of the engine non-destructively, just with using neutrons. We could find out where we were on the engine.
Right.
And that was great fun too. That was John Root and myself. So that was a Pratt & Whitney story, and then it developed, and it developed well long after I left. So John Root and Ron Rogie pushed it further and did a great deal more industrial work, very, very brilliant industrial work, until the reactor went down in 2008, 2009 due to the calandria leaking.
Right.
So that really ended the reliability of NRU as a reactor for doing applied work.
Good.
So one of the things about myself is I'm an enthusiast. So I may not particularly brilliant, but I get on and get things started. So I also started, or helped start, the field in Oak Ridge National Laboratory and Los Alamos National Laboratory. And we did that I did that by taking samples down that we'd studied, and we looked at them on their equipment. So for example, we'd looked at this disk that I talked about, Elaine's disk. So we were able then to duplicate the results in these two different labs, one in Oak Ridge by crystal diffraction, and the other in Oak Ridge in Los Alamos with time of flight diffraction. So that was one of the things I did. The concepts are so easy and so simple to understand that I felt that it was much more important to have everybody doing it and create the field rather than keep things to myself or keep things to ourselves. So I had a hand in starting the work at Oak Ridge and Los Alamos. So in 1998 I retired. It was a year after the change from ACL being the paymaster of the neutron group to the National Research Council being the paymaster of the neutron group. That was accomplished by Bill Byers, particularly because of the discussions he had with ACL management and NRC management. But I was not quite sure of how things were going to pan out. I could retire because, in fact, when we were thrown out of ACL, given the push, there was a year's salary put in escrow for us, so we could retire, and if we retired, we could collect that escrow amount. So that's what that's what I did. I retired in 1998, but I was in a pretty low position because all these things were happening, and Maureen was very ill. So that was 1998. Now, I have a friend at Los Alamos, the person I'd worked with actually when we went down to start their program there, who knew I was in a low spot, knew me quite well, and said, if you write down your CV and send it to me, I'll see if I can get you a fellowship at Los Alamos. So I had a 2-year fellowship at Los Alamos, sharing it with another of my colleagues, a man called Jerry Lander, who I'd worked with before in magnetism, on actinides before, at Chalk River in magnetism. And he and I shared this fellowship, and we shared an apartment together, and sometimes we were both there, and sometimes when neither of us were there, then one or the other. Anyway, it worked very well, and I know Jerry very, very well. So we were called the Tom and Jerry pair. So anyway, I had a very happy 2 years there, meeting a lot of new people, and of course it was Los Alamos, so I was using new techniques, and in particular I was using time of flight techniques. So by that time they designed Mark Burke had designed at Los Alamos a purpose-made instrument to do these kinds of measurements called smarts. And we were able to start using smarts and doing experiments there and making a series of new friends down there with my colleagues. So that was a very happy way that it all started off. So I then my friend Jerry, I'd shared the fellowship with, suggested that I might go to Japan to help mentor a young person who'd just taken over their program at the reactor, the JRR-2 reactor in Tokai. So I went over to Japan a large number of times, 6 or 7 times, to work with this person, do experiments with him on their equipment, and really get things going. Now the other person who was there was a man called Rob Robinson, who'd done inelastic scattering with a chopper at Los Alamos. And he went off to be the director of the neutron group at ANSTO in Australia, the Australian Nuclear Science and Technology Organisation. So he said, why don't you come out and give a series of lectures in Australia about the technique, and we'll see if there's any interest in building a piece of equipment at ANSTO to do this. So I said, oh yeah, that would be fun. So I went and gave this series of lectures, and sure enough, there was an interest in Australia to build an instrument to do this sort of thing, a purpose-built instrument. And I had, I didn't design it, but I had a fair bit to do with deciding that what they had proposed was in fact quite doable and would work, and also had a hand in training, quote unquote, the Australian staff at different spectrometers elsewhere in the world. So we had a lot of fun looking at zircaloy welds and things like that with them to get them up to speed in how to interpret these kinds of results. So that was very good. As a result of that, Canada made a $10 million gift to Oak Ridge National Laboratory to build a purpose-built spectrometer there to do stress-strain measurements at the spallation source. So I was fingered to be the head of the instrument development team, not to design it, but to oversee the design and make sure everything was going to work. So I did that too. In fact, I wrote the science case for building that spectrometer at Oak Ridge National Laboratory. So that was great fun. Spent a lot of time at Oak Ridge too, going down there and looking at how things were going and whether it was all going to work or not, which of course it did. And they have a big program of their own doing that at the spallation source. So then I spent a lot of time going to Australia, to Japan, and basically having fun. I didn't make any money on it, but I had great fun, and my travel was paid for, and I got some interesting experiments done, and met some very fine new young people, and got friendly with them, and really had a great time doing this. So the interactions at Oak Ridge kind of ended in 2008, 2009. Because of the financial crash, there was no more money for visitors in the United States, so that was the end of that. Fukushima dealt a death blow to any work with Japan for visitors as well, because it all went to understanding what was wrong in Fukushima and putting it right. So those sources of entertainment kind of dried up. One thing that I did at Los Alamos, which was quite fun, is they tend to look at rather exotic materials that aren't looked at anywhere else. For example, uranium weld. So we looked at a weld in a uranium tube. It was tricky because of the grain size problem, but we were able to overcome that by rotating the cylinder on its own axis all the time we did the measurements. So we were looking at the same equivalent place through the thickness of the tube, but since we were rotating it all the way around, we got a much better statistical measure of the stresses in spite of the grain size. You could compensate for the grain size by rotating the sample all the time. Right. So that worked very well, and we were able to make good progress with it, partly because the uranium weld has such a strong crystallographic texture. We were able to make some assumptions that were quite viable, and showed what the stresses actually were and how to do it in a uranium weld. So that was very interesting. I still go over to the UK for proposal review meetings, so I've been really very well connected to the UK through that, and people I met on the review committee. So one experiment I was particularly proud of, addressing this problem of measuring stresses in components with large grain size, was an experiment I did with people from the Open University at ISIS doing it. And what we did was, interestingly, if you consider doing a measurement in a sample with large grain size, you may find a number of possibilities that the grains are uniformly distributed within your little voxel, in which case there's no problem. If you do the experiment by bad luck in a place where there's only a couple of grains on one side of the voxel, you're going to get a poor result. So you're going to get a big amount of scatter from point to point when you go through it. Mm. But if you turn the sample through 180 degrees, you're looking at the same point in the voxel, but now the grains are on the other side. Right. And then if you do the measurements and average them, you get rid of that scatter really pretty well.
Yes.
So that was something useful, and that was probably the last paper I wrote with respect to trying to alleviate a problem. One of the other things I did with the Australians, which was quite interesting actually, was they had in their reactor, the Opal reactor, they had some sort of a chimney, like a flue, and there was deuterium on one side and hydrogen on the other. But it was made of zircon-niobium, and they welded it. With zircon-niobium welds, you have to be very, very careful to immediately anneal it, and if you don't, you get a crack. Uh-huh. So they hadn't realized that they had to anneal it when they did the weld, and so they did get a crack. So the question is, how big is the crack? What are the stresses around it like? Would they cause problems in this flue in the reactor? Would there be severe leaks from one side to the other? Lots of hydrogen in the deuterium and so on. So we did an experiment on a mock-up at ISIS, that's at the Rutherford lab with time of flight, and sure enough we were able to measure the strains near the crack that had been created in the mock-up and show that in fact it was reasonable. The stresses were not too high, and that if you overpressured the deuterium slightly, then any exchange you get through that crack will be from deuterium to hydrogen. So you just lose a little bit of deuterium. You wouldn't contaminate the deuterium, the heavy water. So that was a very interesting thing to do too, and that worked out very nicely, using neutrons to solve a neutron problem.
All right. Okay.
So then that more or less brings me to the end of the story. So I've had 57 years of doing neutron scattering.
Yes, I was just trying to do that calculation here.
Yeah, and it's been a lot of fun.
Yes.
And it's kept me well supplied with problems in retirement, which I think is a good thing. It keeps the old grey matter working quite well.
Yes, well, thank you very much for taking us through your 57 years, plus the earlier years of Chalk River that you had researched and that really would have disappeared if it hadn't been for
it would have.
For your efforts there.
Yeah.
Thank you very much. Before we go, we have to just mention also that the Holden Point name in Deep River is also famous for cross-country skiing.
Thank you.
You were certainly involved very, very early, but you had family who were very deeply involved in it, weren't you?
Yeah, absolutely right. So there's two of my daughters, Rachel and Margaret, were very, very good cross-country skiers. And they were both Canadian champions in their age groups when they were teenagers.
Right.
So they were coached in Deep River by Carol Mika and Ross Meadowcroft.
Right.
And they did extremely well. So Margaret eventually pulled a muscle in her back, and the coach didn't realize what was going on, and she distorted her spine. So that was the end of her skiing.
Right.
Eventually she had an operation which reversed that. It got rid of the squash in her between the parts of the spine.
Right.
And she's now fine now, no problem with it at all, although she has to be pretty careful. Rachel decided correctly that being a cross-country skier, even if you were a Canadian champion, was not going to be a job for life.
Right.
And so she decided to go into medicine, and she's now full professor of medicine in the kidney field at Kingston. But she was a very good skier.
Yes. Yeah.
Right. So but we're all still keen on skiing, and I was very keen on racing in those days. But as time gets on, you feel less and less capable of pushing yourself too hard.
Yes, I'll also mention that Tom and I cleared a few kilometers of ski trails over the years as well. And,
yes, we did.
Yes.
Yeah.
Well, thank you very much for sharing both a bit about your family and also about your 57 years. And we hope there are a few more years of that coming yet.
I hope so.
Yes.
Thank you, Jim.